sharing.
Someone is indecisive if you want to.
Yeah, you all dropped out.
Just checking along.
It's not that, it's more the WebEx issue. I thought it's faster because I thought this guy is already on WebEx before I joined on.
Are you sharing your laptop already?
No, I'm not. So that's why I thought the presentation laptop that is dialed into WebEx would be the fast option. But
you want to try it? Your laptop works better.
Well, it has Windows.
That's US buggy for that.
Let's try this. Oh, so I need to activate Office. Okay, so now for PowerPoint for you. Okay, it's on the GitHub repository, right?
Yes.
So we can show it from my laptop. That should work.
Maybe you can start talking.
I'm Matthias Kovac, and I'm now working on some kind of new topics. So the general background is industrial IoT, where we have kind of a different setting than the wireless that we see in the home. One technology that I'm now working with is so-called time-sensitive networking. That's a group of standards that's defined by the IEEE. It's somehow related to DetNet. DetNet is kind of deterministic networking at layer 3. And there's also deterministic networking at layer 2. That's this TSN group of standards. And another background is that the OPC Foundation is having a new activity called field level communications. Basically, so far they have been working on the management level. So if you have your controller, how to get diagnostics, how to configure it, and so on. This could be done vendor independent through OPC UA. But below that, usually you had the typical field buses like Profinet, EtherCAT, and so on. So there you had still whole bunch of different systems that are not interoperable, have basically this vendor lock-in connected to it. And the idea is that OPC UA can also become a cross-vendor standard that goes down to the field level, so talking to devices, connecting controllers, industrial controllers between different vendors and so on. And of course, for industrial networks, you want to have this deterministic activity. And so they base the real-time performance and so on TSN. So we now have two new ecosystems, TSN on top of that OPC UA. And this kind of gives you a vendor-independent stack for industrial IoT. And overall, this is a kind of a good use case for Web of Things, where we try to describe existing ecosystems. And I now have my slides. This was the background. Just here, a small chart. Most of the communication in industry is still wired. They want to rely on it. There's only a small share of maybe 6% wireless. It's growing, but still the rest is connected. So that's why TSN with Ethernet or based on Ethernet is an important target. And one thing is you have to configure this connectivity. I already talked about this FLC, the field level communication activity. So before it was going up to the management. Now it's really going down to the devices. And what I have been doing in this project, or rather a student that is currently visiting, Luca Studio from University of Bologna, has been working on this, how to describe this with thing descriptions, and then how to combine this with the network configuration. To give you an idea how OPC UA looks like, so on the left is a screenshot from a tool that can speak OPC UA. You have multiple nodes there. They are addressable with a rather complex scheme. So you have a namespace that you have to provide. You provide an identifier for the node. And as I summarize here, there are actually different types of identifiers. You can give it an integer number. You can give it a string. It could be something binary. So you have many, many options there. And each of these nodes can be of a specific class. So either it's like an object, it could be a variable, but even methods are typed like this. So you have this strong typing in OPC UA. And another thing is that it's inspired by the web, but it made everything more complex again. So the web was successful because it was so simple. They thought it's better if we have more options and make it complex again. So there are bidirectional references, which was actually why all the other hypermedia systems died out there and the web succeeded. You have to deal with bitmaps, you have to deal with word sizes when you communicate data. This is where a lot of friction is created. If you want to describe it with newer technology, if you look at CBOR or JSON and so on, you don't care about how many bits a certain integer has on the end device.
Is there a standard URI scheme for nodes?
So OPC UA hasn't filed anything with IANA. In their own documents, they always use opc.tcp or .udp, but that then only has a hostname and port to identify the entry point to an OPC UA server. And from there, basically nothing is defined. One thing that actually comes here when we want to do the mapping, we have to find out what fits together. And on the last line, you see that we have to have a combination of the server address, the namespace, and the node ID. And this is something that we then can put in there. Later, I will talk a bit about what are different options we have and so on. Otherwise, I mean, from a high level, it looks quite well. So if you take an OPC UA server plus some so-called PubSub functionality, that would be something that corresponds to the servience in the Web of Things. In the FLC, there's something now defined called functional entity that pretty much corresponds to a thing in our sense. If you have variables, they can be treated like properties, methods, actions, and something that comes in with FLC more dominant, but is actually also available in the existing specification called PubSub, are data sets that are defined and regularly published. Those basically map to events. The other ecosystem, I already introduced TSN in my stand-up speech. So there are a lot of these ugly abbreviations. It's all built around the IEEE 802.1q standard. So that's basically the standard that defines VLANs and switching, so bridges, endpoints, and so on. And basically the VLAN header is used to encode priority and some additional information to manage this deterministic traffic. So how does it work? So the blue boxes are switches here. We have a bunch of different end nodes. Basic capability, what we are currently using is if you have end devices that are not TSN aware, you can still reserve bandwidth between the switches. And if this is like the only Ethernet cable, you have one application here. There is no interference. There are no other applications talking or stealing bandwidth. You'll find here. And then on these trunks where you have to share actually the cables, there you can reserve the bandwidth so that those endpoints still can perform in a certain way. And for instance, if you have cross traffic, important signals like control messages and so on won't be dropped by the switches because they have reserved queues. And you also have a model how long it would take between the switches at least.
So basically, I'm sorry, these are gateways, routers, these endpoints where the traffic gets mixed.
These are switches. So I'm talking about IEEE 802.1. So this is Ethernet. Those are Ethernet switches.
This is what you're saying. So TSN needs a guaranteed latency. Yeah. So we have to guarantee, a certain time slot.
Yeah. So I'll get to more details.
TSN still has to make progress in the long run, right?
So I mean, the point, the situation at the moment is you don't find on the market TSN-enabled endpoints yet. So mostly it's prototypes that you find. Often they're even still FPGA-based. If you have a TSN-enabled end device, they can do way more. They can basically sync the application to the network access, and you can have a real deadline guarantee. So you can also define how much should be the jitter, that your message arrives early or late. So you have basically what is often called isochronous network access in the industrial network. So basically that the application is even aware of the timing in your network. And how is this done? So in these switches that are TSN capable, is that they basically have 8 different queues to store these packets, and each queue belongs to a certain priority that is defined in the VLAN header. So therefore there are 8, and you can assign then specific traffic to a specific queue. And what you then can also do is you define certain timestamps when the gate for each queue should be open and closed. And this way, basically, you get something indicated here at the bottom that you have some kind of time dimensional multiplexing to access the Ethernet medium. And one thing is either you divide it by traffic classes. So that means that multiple frames from multiple applications get one reserved window. You can also do something called frame isolation, where then basically a single application or a single frame gets its own window and will be delivered. In detail, that of course is then also getting a bit more complex. If you have multiple switches, you basically have to grow this time window because there's always some kind of jitter. So the state of the art is actually rather pack them together. Overall, you get better performance.
Now the basic mechanism is queuing. There is no physical division of frequency to the isochronous channel.
No, it's time-based. Yeah, it's so at the moment, I mean, there are different things. So this all started with audio-video bridging, where it was basically traffic shaping with the so-called credit-based shaper. And now there's a time-aware shaper where you basically use the precision time protocol to sync all your nodes and then have the time multiplexing to reserve.
Yeah, that's it. Because 20 years ago in IBM we did isochronous by dividing the bandwidth and 6 that was reserved and circuit switched.
No, so the main point here is that it's actually still allowing best effort traffic. So if you have these nodes, your IT nodes and so on, they can still share the same cables, the same infrastructure. So because of that, TSN is also a technology that allows you to really converge your network so that all your IT infrastructure in a factory, for instance, can use the same cables as your control infrastructure.
Question.
Okay.
He raised hand.
Yeah, then.
Let's go ahead.
Okay, I have just one question.
We can barely hear you.
So, yeah, I'm working for the W3C media buzzer, and they have also been about
Cas, could you wait shortly? We have to crank up the volume. Okay, go ahead. Yes.
Okay, thank you. So I'm working W3C. How to manage
It's not deterministic.
It's up to here. Some collaboration might be used.
Yeah. You're not talking in the chat room. Cannot hear you.
If people are talking at the moment,
Maybe chat.
loudness, I can't.
Okay, so
pull up, yes.
maybe you go ahead and run class types in the chat room.
Okay. Then Ari, can you basically take care of relaying? Sorry, Cas, the audio was completely broken. I'll quickly continue. And if you can write, that would be great. Okay. And to manage these networks at layer 2, there are different approaches. The one I'm showing here is the centralized model. There's also a distributed model using different protocols. And then, of course, a hybrid model that combines these two approaches. What has to be done, basically, that you have some entity that can talk to your applications and can collect basically the requirements, the quality of service parameters of the applications, and then talk to a networking configurator, so the network controller, that then basically translates the quality of service requirements to a certain schedule. So these gate control lists that I have been indicating to reserve resources on these switches. And this central controller is then talking, usually using netconf, to these devices. There would be other options like restconf. We are currently working on coreconf. but for some reason I found that netconf is kind of the de facto standard what is deployed on this kind of network equipment. RESTconf I have only seen as at SDN controllers northbound to configure this. And in short, basically what we also need besides an OPC UA binding to make this part of the web of things is, in this case, a netconf binding to talk to these switches. Here, the mapping is also possible. So we have a proof of concept implemented. Luca did all the work here. So if you have the overall stack on your embedded device, that would be the servient. We have then the running netconf server that has multiple data stores. This could be identified as the thing. The leaf nodes in this model, so usually it's a Yang model that you have deployed there, would be the properties. Yang also supports RPCs. Those can be mapped to actions. And you can also have notifications in this model. And there we are with the events. And basically, you have an XPath, because it's XML-based netconf, into this data store describing nodes. So this is what we then take basically for the href part to build a netconf URI to address the individual parameters. This is how the messages look like. As I mentioned, it's XML-based. There's a lot you can ignore. There is basically under the RPC a node that identifies what is the method that you want to apply. There's get, there's edit config, and then you can define custom RPCs to do something on the data. And there's some or multiple choices. Actually, one way is to basically build up nested nodes that correspond to the XPath to describe what you want to change. And the same thing is also if you want to write to something, you include these nodes and then have the actual configuration data embedded there. There is one pitfall is that there are actually multiple data stores. So one is representing what is really running on the switch. There's a candidate store where basically you can first do a multiple configurations and then do a commit to atomically apply a new configuration. And you can also read out what is the startup configuration. So when this thing reboots, what will be the default configuration. This then leads to a number of design decisions that we had to make for the bindings. I think I won't go into detail here. It's on the slides if you're interested. The main takeaway here is, so we have a lot of options here. I marked some of the not so good choices in red. We did the same basically for OPC UA. If you have these existing ecosystems that are, say, built in a different time with different ideas, different mechanisms, it's getting quite hard to apply Web of Things. And I think this is actually an exercise that has to be done, that we look more into these existing ecosystems and concentrate more on the complicated cases to really understand, do we have everything covered? Is there something missing? And there are always choices. We basically drop a few things.
What are the configuration parameters that we're talking about for OPC UA? Slots?
So OPC UA is basically, we get some standard layered model for industrial IoT, and OPC UA would be the application that is basically something that would correspond to the web with HTTP or to the core ecosystem. This is nothing that is it's modeled in Yang or whatsoever. OPC UA.
What I'm asking is, I guess what I'm asking is, why is OPC UA on the slide here? What does it have to do with that?
Okay, so so the starting point was, at the moment they are all different kind of vendor-specific protocols, and there are some convergence going on. And the main convergence that we can see at the moment is that OPC that has really a broad base, a lot of vendors are in there. They are now specifying something that can work at the field level, and to have deterministic behavior at the field level, they build on top of TSN. So to get basically the full stack you need for industrial applications, you use TSN as the basis to converge the layer 2 infrastructure. And on top of that, you have an OPC UA field level communication to also have convergence at the application layer.
Okay, legacy field classical.
Yeah, so all the big vendors are in there. So things like Ethercat, Profinet, and so on, they are expected to be superseded at some point by OPC FLC.
So the real question, so will it be OPC FLC that delivers the appropriate TSN TSN slot information, or will that happen below?
So actually there is, I didn't want to go into too much detail. There is a step in between, which is the IEC IEEE 6802 working group. They are defining an industrial profile for TSN. Within that, you have different kind of classes, and but this is basically the definition. What will be the parameters, the selections, and so on. What an industry application should be able to configure at the network level.
So my next question is, how dynamic is this device? You expected to have this based on its structure, or is it configured?
It's really configuration. So basically, usually you buy a PLC. So it's multi-layered again. So I guess we are going in a slightly different direction, but I think it's also interesting to look into industrial IoT. So usually devices you can buy off the shelf, and you just plug them in, and then they get minimal configuration, but you don't have to do so much. Controllers, on the other hand, you usually need an engineering tool where you then basically install a software or model the software that should be running there. So that is then really dynamic. And the main is then going on in the engineering where you say which controller should talk to other controllers, which controller takes care of which device, and so on. So you get a lot of these so-called application relationships when you apply these kind of off-the-shelf components to produce either a car, bread, or whatsoever. So it's something that overall is probably done once at the design time of a factory. But what you see nowadays is that it becomes more and more dynamic. So batch size 1 is one keyword here. Other things are that you want to evolve more easily and reconfigure, add new devices, for instance, to have some predictive or preventive maintenance use cases fulfilled and so on.
And so but there's signaling tied to this, right?
Signaling, sorry, what you, I mean.
So in terms of, assigning slots and then
so it is implemented and realized at layer 2, but basically who has to talk to whom is defined at the application level where the engineering tools come in.
Question as well, the data schema extensions, same issue arises up to the 1 data model. And like bit, and it'd be nice if we could coordinate our efforts here to the model.
Yeah, so I mean, this is a side project. It's a visiting researcher doing this currently in our lab. We are working on a paper on this. So maybe I just go on with my presentation because I actually cover this. So this is the overall setup, how it would look like. So you have your devices in the field. So for instance, some sensors, an actuator, something that is an actuator, but also provides you with information about a certain position, for instance. You have your TSN fabric there, and somewhere you have your application. So this classically would have been a hardware PLC, so programmable logic controller. Now you often see soft PLCs, virtual PLCs running on edge compute nodes. And for instance, our Servian could be providing something like this. And what we implemented is basically the actual mashup application. So this is telling the equipment what to actually do. And we have implemented a TSN controller app that basically takes the quality of service requirements and turns this into network configuration and is able to push it out. So the workflow would be that the mashup application fetches the TDs from the devices as usual, but those are then enhanced with these quality of service capabilities of the infrastructure. You then match these capabilities to your actual quality of service requirements. So basically the application has to decide how often, for instance, you want to update the position of the robot, how fast as the transport system should be controlled, how often you want to read out the positioning from the sensor, and so on. And once you have made certain choices within the bounds of the quality of service capabilities, you can talk to the controller app. That one tries to push out the schedule. So first it has to translate and actually calculate the schedule. That is a NP hard problem actually to come from the requirements down to these gate control lists. So there is a lot of investigation, network calculus, and so on to actually do that. Try to push it out and then basically report back if the setup worked. What are these quality of service parameters? So for instance, devices often have a minimal interval to actually be able to process data that is coming in. Message sizes are important to do the allocation on the network. You want to know, for instance, a send offset. So the time between the sensor reading is taken and when it hits actually the network. You really want to have a tight timing here, down in the microsecond range. There might be some receive offset. So if I send a command, know the network delay, how long does it still take in the device itself to actually apply that? And also, what is the clock synchronization? What is the mechanism? There are several standards actually out there. And on the side, on the requirements, as I said, the application knows usually what is the maximum interval. So how fast must this actually run to fulfill its purpose? What is the overall delay that is allowed, that it won't crash, for instance? What is the receive offset? So this jitter that has to minimize. And this is probably not complete. So we are still collecting this, and yeah, hopefully have a good list in the paper later.
So this QoS requirements for the thing, are they supposed to be specified by the application writer, or are they some inherent properties in the thing description? In the thing description.
Yeah, so my hunch, or what I try to establish, is that these are basically capabilities of the things. So if I produce this, I know what is the hardware capable of. So actually I have to dimension this, that a robot, for instance, is able to really quickly process this. A sensor has maybe a lower one, and then what is possible by the hardware and so on is described here. And the application, of course, then has to also choose and decide based on this what is possible.
So if I understand correctly, what's going on here? As we say, this is a static thing, right? This is information that the TSN controller needs in order to establish how to meet these requirements.
Yes, indirectly, because the TSN controller itself wouldn't be able to actually work with this. It still needs this translation step to really work on a network cycle, gate control list terms, and so on. But yeah, it's a different kind of representation of the same knowledge or requirements.
Okay, so this is used to essentially produce information for the network, if you will.
Yeah.
Okay.
Mainly for the application, actually, and the application then can make the decisions and then have a resulting requirement to make this run on this infrastructure. And these quality of service parameters are then translated to something that would be pushed out via NetConf, for instance.
Sorry, but since we heavily underestimated how much discussing what our station.
Yeah, I'm almost there. I'm about to conclude.
It's a good presentation. Very good.
So here, this is just for illustration. I mean, you would need to import a new vocabulary in your TV. There are some global definitions, so that this is basically device level. For instance, here that the .1 AS ref mechanism is used for time synchronization. What is the minimal interval? Then there are some at affordance level and maybe some at the form level. So basically, because the maximum message size over HTTP will be different from co-op, for instance. I'm still not sure if we are, ideally we can give frame sizes, so layer 2 information here. Maybe there should actually be more abstraction. But if you really want to calculate in the end, you need to know how big is your frame really on layer 2. One issue is that we don't have a mechanism to actually give such metadata for applications. So far, we didn't define any container formatter whatsoever. There's, however, some ongoing work. So we looked, I think it was in an EU project or something. OSGI has something that they use, which is the requirements and capabilities document that they have. And also for network function virtualization, you have these kind of descriptions, what are the requirements actually for this application to run, what hardware is required, and so on.
Yeah, we're looking at packaging application WASM.
On
WASM, we're looking at you know, how do we encapsulate installable software.
Yeah. So to conclude, I mean, TSN is quite interesting because it really allows convergence there. We need these quality of service parameters to have requests sent to the TSN controller. Maybe side info, TSN is also investigated for wireless solutions, so TSN over Wi-Fi, but also 5G is a topic there.
There also will be a role of
Probably, yeah. I actually have to catch up and see what else is going on there. which is pretty obvious. TD can provide the semantic information there. This is, I mean, a first step. And I was quite happy to see that this topic, which I wasn't even aware of when we started this project, that semantic description for connectivity is actually a topic. So TD can also help there. And we are doing the first steps in the paper that we plan to publish. And another issue that we saw is that basically if you want to do these Web of Things bindings, the devil is in the details, and we need to make way more efforts there to figure out what do we need to fulfill this vision of convergence and have a uniform description of this all. There are some other pointers that we could discuss maybe offline at a beer or whatsoever, and I will cut it from here.
Matthias.
I don't know if Cass put in his question.
Yes, I got quickly. So it was a comment. Read it out.
Yeah, I've already put some comment on the minutes.
You want to read it out yourself? Okay, I'll read it out. So, because Gus was saying, working for the WPC.
Can you hear me?
Yes.
Okay, so I changed the headset, and yeah, as I mentioned, I've already put my comment directly to the minutes.
What is your comment?
Yeah, that was just that I've been working on for the WCC media rated groups, and they're working on multiple video streams and synchronizing those video streams. And from WT viewpoint, I think those video streams bit-based yeah, data stream and yeah, or byte-based stream, and how to synchronize and deal with multiple streamlines would be, yeah, useful for this discussion.
I think quality of service shows up in media delivery. It also shows up in web and networks group W3C.
Yeah. It's related to web and networks as well, and originally media and entertainment industry group.
The real question is this, like QoS extension, usable in other contexts? How general is it? Is it really specific to field processing?
Yeah, so I was focusing on this TSN capabilities, which are really for control traffic. As I mentioned, this is an extension to AVB, audio-video bridging, where they started. So it's a good use case to also look into the multimedia part.
Yeah. And actually, I proposed during the TPAC meeting in Fukuoka in September, the WCSWT group should collaborate with the media-related groups and networking groups, yeah, about how to deal with video stream, AV kind of video streaming, yeah, based, yeah, for example, using some specific event sets.
Okay. Thanks, Gus. Unfortunately, we need to move on to the next topic. So we actually have minus 30 minutes for mud and ice together. We were planning to have the last half an hour for wrapping up and concluding everything. Maybe we can squeeze that into like 10 minutes, which would give us 20 minutes for both. How you guys wanna? You both.
We'll just keep going and see how it goes.
Yeah. We have until 5 here. Now it's 4 o'clock. So, yeah, maybe try to keep it a bit shorter than we originally anticipated. And then we have 45 minutes, like 2020.
Oh, okay. Discussion has been going on, so let's see how it goes. You have my slides. All right, so I'm going to talk about manufacturer usage. This arose from a problem that all of CIS customers are having. That's one of our customers. Is they're being inundated with IoT devices, and they need to know a little bit about them. So, what is it that they need?
You wanna maybe click your way through here.
Yeah. So I can run off that if you want.
I'll be going taking notes. So
Okay.
if you wanna.
So, is there a clicker?
Yeah.
I could just use this.
Spare USB.
I could just, it's okay, we don't have to. All right, let's just see. So, today's problem, right? Let's talk about printers just for a moment. Okay, these actually,
It's not IoT.
oh yes, it is. Okay, but in fact, it's probably the earliest IoT. Because printers have been networked since Harston was a young man.
Well, no, that's not.
And they still don't get it right. And why should they? The rest of us don't get it right either when it comes to security. So, you know, that's the problem. Now, just, you saw a little cheat there, but would anybody care to guess what sort of access that printer really needs? It's good. I'm sorry.
They're getting smarter and smarter.
You would be crazy to guess. Because this is a short version of it. Now, we're geeks in this room, okay? Check it out. This HP printer uses Jabber. Okay? So it's using a chat protocol. Right? Who would have guessed that? Who gets to say what the printer gets to use? The only person who gets to say that is the designer. Okay? Not Cisco, not Huawei, not the W3C, the designer. Okay? So how is the core administrator even to discover this? You can sit there and listen quite a long time and try and figure out if he's gotten all the exception conditions. And this is one device, right? This recurs throughout the market, right? And however many types of devices there are, right? The administrator has to go and do that in order to figure out what sort of access a device needs. Now, why would anybody care what access a device needs on the network? The answer is these devices cannot possibly defend themselves. They don't. They try, and they should try. They should keep trying. They should do better and better. But there are always going to be zero-day vulnerabilities. And so it's important that the device manufacturer employ an additional layer of protection, and that's where the network comes in. Not to trust the network in terms of its access, but to provide the network with information such that the network can defend the device. That's the purpose. And this occurs across all markets, smart cities, industry, consumer, you name it, it's there. My cousin, and I'm sorry for taking part of my 20 minutes to tell us, my cousin just got a smart oven that woke her up at 5:30 in the morning to tell her that it needed to be cleaned. Okay. I asked her, why on God's green earth you would allow that thing to be networked when just to tell you that it needs to be cleaned, when it's actually a threat to the rest of her environment. And there is no protection. So this is where manufacturing usage comes in. So let's talk about assumptions and assertions. From an assumption side, we say a thing has a single or small number of uses. That's my definition, part of my definition of a thing. It's not general purpose computing. I'm not trying to solve the problem for an Apple. Okay. Things are tightly constrained. They have very little CPU, very little memory, very little battery. What's not on the slide and is most important, they have very little programmer time. That's the most precious thing. So any solution that we propose along these lines has to be simple and has to take very little time for programmers. At the end of the day, no matter what solution we propose, the network administrator gets to say what sort of access the devices will get. Not Elliott, not Cisco, not Huawei, not Juniper, not the device manufacturer, but the administrator. And let's also assume that any device that claims to be secure, any manufacturer that claims their device is secure, is lying or doesn't know what they're talking about. Okay. Based on that, we have a couple of assertions we can make. Because a thing has a single or small number of uses, therefore we can enumerate those uses. And the people who are best in position to enumerate those uses, because there are a single or small number of uses, is the manufacturer themselves. Right? And the mechanism needs to protect devices that may have vulnerabilities. So this is not really technology, conveniently. We've had access lists in the network since Carson was a young man. That's so deep. So so the only question is, how do you choose the right ACLs, right? So we introduced 4 specific new architectural components that into the existing environment. The first is a URL. Let's note that this is 1993 technology, okay? The second is a MUD manager, which we're going to associate with the AAA infrastructure, but you can just as easily associate it with other components within your network. The third is a description file, which we call a MUD file, manufacturer usage descriptions. It's JSON. It has a couple of, it's based on a Yang model. And the fourth is a MUD file server, which we will call Apache, which sits somewhere out there and delivers these MUD files. So here's the flow really quickly. Device emits a MUD URL in some way, shape, or form, or it is otherwise learned. The network's going to pick that up, send it over to this MUD manager, which could be an adjunct to your AAA server. Okay. The AAA server sees a URL. What's it going to do with it? It's going to do what it does with URLs. Looks it up. Goes to this file server. It's just a file, right? That's what it looks like. This is the actual new part. That's newer than 1999 technology. Here you have some JSON. And what we've done is we've taken the access list model. We're configuring the network. So we're configuring network access. So we take that access list model, abstract out the IP addresses. And in some cases alone, we need to fill in, we provide a template for the administrator to fill in some information as to what sort of access is needed. That then gets shipped all the way back into in its instantiated form into the network once an approval step is happened, because the network manager is the queen of her castle. And then the device is then microsegmented. So you provide the appropriate network access, so the lighting switch can talk to the light bulbs, if you will, and a thermostat can talk to an HVAC, for instance. So the administrator doesn't play guessing games, right? You get determinative policy, declarative policy, and the device is relatively automatically segmented. This saves us from the fact that we're running out of system administrators on this planet. This is the problem that manufacturer usage descriptions to describe. One of the earlier routing area directors at the IETF was Michael Dell. Said the only problem we ever have to solve is scale. This is what we solve. Can't really just throw out an RFC. Got to have some tooling. So starting with policy developers, the way this is being rendered is a little weird. We have something called mudmaker.org. And so you can do some policy authoring. You can go to mudmaker.org, click on it today, and you can try this out, right? You can take the result of the MUD file and then visualize it. This is cool. This is I have a grad student who did this for me over the summer. You can just visualize it. Pretty cool, right? And then we have some tooling that implements it. So this is an example of a template. Here, one of the things that MUD does, because it abstracts out the way that the access is managed, you have your choice as to how you're going to deliver the access into your network. It can be through normal ACLs. It can be through OpenFlow. It can be through source group tags that Cisco offers, for instance. This is the tool that we show here, right? So, a couple of important points. The first of which is MUD configures the network. We're not configuring devices. There are no new control interfaces on the device. In fact, if you can bind a MUD URL to a device out of band without, say, on a label or something like that, you never have to touch the device at all, and you can brownfield it, right? The device, therefore, requires no semantic understanding of what a MUD file is. The manufacturer does, but the device does not, right? So very little processing, right, on the device. All it has to do is emit the MUD URL, and because this is component architecture, if you can get the MUD URL without the device emitting it, that's fine. A good example might be LoRaWAN, right, where you have a table of keys for each device. You have a device key table. You You could add an additional column for my URL. Works just fine. You could do that. Component architectures are cool. Okay. The other thing is you can use what you want. You could discard the rest. That includes, you could decide that all you want to do is take this for classification purposes. You only want to classify the device. You want to know what's on your network. Maybe you just want to make your own policies. Never mind what the manufacturer is delivering. Okay. You could also not even bother imposing access controls. You could just simply use the information for auditing purposes, which I expect some people will do. You could perhaps take the MUD URL in via bomb import, right? Or that's bomb import for that matter, right? So the other key point here is that MUD can provide no more capability than what the underlying network provides already, because it's merely a network management level issue. So if you have no access control mechanisms in your network, you're not going to get access control just because you're using MUD. Fortunately, most modern routers and switches have this capability, so MUD's pretty generally applicable. That's sort of cool, isn't it? So we've done a lot of work. We've focused on LT access primarily. We want to do, there are different abstractions. I haven't gone into that from a MUD perspective, but there's the controller aspect, use same manufacturer, there's cloud-based, domain name-based access that's provided, and a couple of others, right? Just one or two areas we need to improve for automation. We already have some internet drafts to do that. I would like to see a little bit more better integration in the consumer space for MUD in particular. Michael Richardson has been working on that with the Sierra project. They were all at Montreal with us at the hackathon. We need to look at reporting tools. So manufacturers can do this policy authoring, policy visualization. Now they need feedback to know whether the device is actually gaining the access it needs to gain. And we need to work that problem while being privacy sensitive. Okay? So we have pretty good functionality in 802.3 and 802.11 networks. I'd sort of like to expand that out to 802.15.4 networks. And we've been talking about how to do this with 3G, 5G as well. No reason it couldn't be done for LoRaWAN. In fact, we've contemplated exactly how to do it. And then we're looking at various different extensions from us. One of the ones that we're looking at is TSN. So what, in your presentation, we talk about what device declares. Well, who's it declaring it to? It's declaring it really to the network. Right? The network needs to be configured. Well, that's exactly what MUD's for. The only difference between what we propose and what's here, right, is merely the syntactic sugar around it. Right? So you could do just as easy, you could quote just as easily. And the interesting thing about this is that you need to add no new interface mechanisms for, say, Web of Things in order to deliver that. Now, Web of Things is important when you have thing-to-thing communication. It's less important when you want to inform the network about the way a device is designed. You don't need to have any sort of interface for those when the device is static is designed.
I just want to comment that still the application is quite important. There's other work out there. OPC-based solutions, for instance, are also promoted. What I presented was just an explore, so what if we apply that? But there are also other application-centric how to do this. So I guess it's the question, what is the universal interface that is already available? Right. For industry, often it's that there's some OPC client or server available.
It's possible you can go around, but you can go about that way as well. The other possibility is simply you rip the information out of that interface. That would be the intent. How the network, there's no promises made by that. No promises at all that the network's configured at all by that.
Right. So you could potentially emit a MUD, get the others, and then apply it.
Absolutely.
So then my next question is, so originally,
and I expect that, by the way, to happen as well.
Yes, I mean, I would assume that. So my next question is, so whenever I received, there wasn't much then again, that's pretty much it. So I'm not wondering why exposing the mud file as a core feature.
The only reason we don't do that is that we don't assume any particular capability in the device to provide a file. And the reason we assume we didn't assume that is that the first assumption we made is that devices are really tight on memory, they're really tight on CPU, and they're not going to be able to provide it. That having been said, one could easily extend mud and say, I've got my own mud file here. But there's another thing you have to be careful about as you deliver these. DHCP and LLDP, as defined in the draft, are sort of second best as a way to get the mud URL. The way you really want to get it is via either out of band or certificate. And why a certificate? Particularly a manufacturer's certificate. Because you want the assertion about what the device is, not to come from the device itself, because that's a self-assertion. One is for that assertion to come from the manufacturer to say, this is a seamless deal.
Sorry.
Who is so individual?
So if the certificate lives on the device, whatever, right? The point being that you need that assertion to come. A certificate is a convenient way for the assertion to be made by the manufacturer, where the assertion itself lives on the device.
Well, certainly, mud file would be signed by the.
It is.
Should they do that for software updates?
It is signed.
So, but the benefit of having the mud file now is mud file server.
Yeah.
Moreover, you could expose it as a /mud resource and discover it. You could have resource type like mud.
Right.
So that it would be much more integrated.
Write it into the draft. I encourage you to do it. Right. And actually, I'll give you the code that you can send out the mud manager to take.
What I'm interested in is where we can converge the problem of discovery of TVs to the problem of mud. And it seems that one fundamental issue is identifying the type of device in a secure and higher fashion. From the type of device, you can then indirectly find the mud file and maybe find the TV type or the SDF file. And then it's almost like TVs and muds are in some ways complement each other.
They are. In fact, let me tell you a little bit about that. Okay, and this is why I asked the questions I asked earlier. Right? If I'm discovering the mud URL out of band, I might as well have an extension that simply points that could point to a TV. Right? It will not have identity information about the device. It will not have a specific instance ID in there.
We could certainly also conversely link to a mud file from the TV.
You could.
If you discover the TV, you can then find the mud.
I encourage it. So this RFC came out at the beginning of the year. Okay. This is a stretchable concept, right? The only bounds of stretch that I see are these two. The first is that a mud file is intended, at least as I see it, to not be unique per device, but to be unique per type of device. And the second bound is that the mud file should probably configure the network and not the device or the devices in any way.
But it's about
it's about how the device was designed. It's a declaration.
Network compatibility issue, for instance, if you're the there's that just know that the network is going to be and then the device said, well, but I was not supposed to talk through switches. I was supposed to talk but I don't know switches. I don't know how.
So keep in mind, this policy is abstract. The policies are like, I want to talk to my controller. I want to talk to the same devices, the same type as me. That's the level that you get. How the network implements that is up to the local deployment, right? So the mechanism to the mechanism to implement can evolve over time. Also, the device may gain new functionality, and the MUD file has in it essentially a timer or a cache value that says, go look up to see if the MUD file has changed periodically. So that way we know if there's new behaviors that should be added. So those are a couple of approaches.
It also implies that the software version is part of the device type. You take the software, which is a new device.
Right. Now, this is where you guys in the chip business are really going to help me out. Right? Because I've been banging my head on this problem, but I know that you guys in that industry are looking for ways to update, say, a certificate based on the hardware configuration. Now, the key thing for me in the long term is that I don't want the device to assert this. I provided mechanisms such that the device can assert it now, but I really like to avert those out. But my manufacturers who I'm dealing with will never show up in this room, right? It took me 2 years to get them to emit a URL. That was, that's how difficult it was just to use LLVP, which they were already using. Right? So one of the goals here was to use existing interfaces, because adding new interfaces on devices, apart from programmer time, is also very dangerous from a security standpoint. So I have taken up way more time than I set out with. I apologize. I will take questions maybe out of it.
And Monday there's going to be a side meeting.
Oh, the Monday side meeting is mostly about onboarding. But I'll be at the hackathon tomorrow. Come at me with whatever you have. If you want to hack co-op with me, let's hack co-op. I'm okay with that.
Comments on the slides. We really like slide numbers. And we don't like Cisco confidential.
I'll send you an update.
Can supply an update with all that.
I can supply an update. You're recording the Benoit place. Okay. Cool. I'm actually on time.
I think cannot go back and reflect.
I feel good.
That's on one thing.
Yes.
Ellie, can I have the program?
I think it's on the table there.
So whoever is online and sleeping right now,
All right, no. Sort of have.
yeah. Prepared for 3 a.m.
Good.
The moment
It's allowed to talk about
Yeah, okay.
Let's
So
start.
anyway, so the thing, those of you who've been around for a while have heard about this thing nice before. I talked about it for the first time in 2016. I talked about it in 2017. The difference between then and now is that, first of all, the use case we were talking about at that time was kind of what the original ICE was also designed for, more like real-time media between two devices. And we really didn't see a use case for that for IoT, at least not then. And that's not really the use case focusing here this time either. Now it's more pure co-op or whatever protocol you're going to choose. I mean, I'm going to present how it's done for co-op. It's a generic concept, so you can use it for anything. So this is more like when you have a resource director, for example, see these resource names, devices which are behind that, so you can't really use the resource. Other thing is that also we're looking at it because there are some interesting semantic aspects from here, which I'm going to show with the implement regarding to resource names and resources itself, and how it is done. So basically, one could give a long presentation about ICE. So I'm going to give a very short introduction. I mean, if you're had a lot of questions already. You're leaving away a lot, you're simplifying things and so on and so on, and I do that on purpose because this is not really about ICE. This is just what you need to know in order to, hopefully, need to know in order to. So what ICE is about is finding connectivity. When you have a device, and both devices may be behind NATs. Try, which means that if you're behind a NAT, I will not be able to contact you using your host address because it's a private IP address. So ICE is about finding IP addresses which I can use, or at least try to contact you. So one IP address, the most typical one, is that when you establish a connection to a public network via NAT, that NAT is going to create a binding, and that binding is going to have a public IP address port. So and then I can try, if I know what that is, I can try to contact you using that one. That's a basic.
What does the ICE acronym stand for?
Interactive connectivity established, interactive, something like that. Yeah. And that's basically what a candidate is. Candidate is, I mean, it has a little more data, but basically what it is an IP address and port that I can try to contact you. There are different types of candidates. As I said here, it's even your local address is a candidate because maybe you're not behind that. And then of course I will be able to use it. But there is also this. Oh, sorry, the one I want to mention, the NAT assigned public IP address port, which is also called a reflexive candidate. I'm going to use that word later on. You can also use relays. I'm not going to cover those in this presentation. Then what you do, ICE, is that what the device does, let's be close to the microphone. Oh, sorry, yeah, I want to wait you one. Okay. So what you're doing, what an endpoint does is, of course, in order for you to know what my candidates are, I have to inform them in one way or another to you. And in order for me to inform you, I need to find out what they are. Now there are some cases you have this TCP and protocols where you know I can control the NAT and then I will get that information. But in most cases, and you don't have those, and in IoT you're probably not going to have those, at least not in constraint. So basically, you're going to fetch it. So you're going to fetch this. In ICE, you have specific protocols for doing this. There's a protocol called STUN. And you also have specific infrastructure for this. You have STUN servers. You have something which is called term relays. STUN server, and then I'm going to show a picture of what those are. Then you're going to create these candidates, and then you're going to distribute them in one way or another. ICE doesn't define how you do it. It depends on what signaling protocols and what you have. For SDP, those who are familiar with VoIP, session description protocol, which is probably the most common protocol for distributing candidates. And then when you receive my candidates, you're going to see whether you can contact me using those. Here you have an example of this server reflexive candidate. The endpoint is sending some kind of request. This would be a stun in normalize. To a server somewhere that would be a stun server, and this is actually here you have the NAT. This is the public IP address and port created by the NAT, which is called the server reflexive address, which is the address that the server is seeing. That's where when he gets that request, this is the IP address and port that he sees. Then he can return it back to you, and you're gonna know, okay, this is my candidate that address. That's what's ICE. So what is thin ICE? It's basically the usage of COP protocol and infrastructure to implement ICE. And again, you could insert another protocol here if you want to, and you could define it for this. Here is kind of how you're doing it for COP. And the reason why you would do that, because if you have constrained devices, for example, you may not want to implement this, or you're not able to implement this stun, for example. You may not, if you already have your co-op infrastructure, you don't want to deploy these stun servers and everything like that. Maybe you already have them and then you may be able to reuse them, but in case you don't. So basically, thin ICE, it's applying ICE on co-op or some other
constrained protocol or protocol for constrained devices. No, here I'm looking at the same steps which I described for eyes. First, you're going to fetch this or get this candidate so you can distribute them. Now, instead of stun, we're actually going to use the co-op protocol here, and we're going to use a co-op resource. Then to create the candidates, nothing strange there. You do it in the same way. And then when you're distributing them, we're actually going to use the co-op protocol and the resource directory and resource links. I'll show you then how it works. So everything you see in bold here is things that you already have if you have a co-op infrastructure. So you don't need to add anything extra if you want this as a version. The first thing you do, and this is how you're going to fetch these addresses. So basically, there's going to be, I talked about you had this server in the network where you send this request, and he looks for the IP address where it comes from, and then sends it back to you. You have the same thing here. We call it a T-stun server, but basically, it's just a co-op server which hosts a resource, a dedicated resource, which we call reflexive resource. And the only thing what's going to happen is when you send a co-op request to this resource, you want to read the value of the resource. Server is going to look where the request came from, the IP address and port. It's going to assign that value to the resource, and then it's going to return it to you. So this resource will actually get its value when it receives the request. Then if you have you may have multiple devices communicating with it. So it may get requests from another one, and then it's going to assign the value from where that request comes and return it. So this is a little different than normally resources, because this will get the resource value when it receives the request, and then it's going to send it back. And then obviously now you have sent this co-op request through the NAT, so you need to maintain the binding also open. So then you can keep sending this every now and then, depending on there are different ways to find out how long the NAT binding is going to stay up. And the good thing about that, because if it happens that the NAT binding goes down, then you will see, because it's every time going to return you this reflected address. And if the NAT binding for whatever reason has gone down, then you will see that, because next time it's probably the NAT is going to create another IP address and port for you, and you will get that back. Yeah. That's the first thing. And here you have a picture of this. You send a GET request. You have the reflexive resource, which is its address to its T-stun server, and it sends back, for example, a 205 content. This is the address which is here, which you read from the request and sends back to you, and now you have it. So now you can distribute it to some other one here who wants to contact you. Now, how are you going to do that? And this is in two parts. First, you have this the one hosting the candidate or wants to distribute it. The endpoint, the hosting candidate, and there's two ways of doing this. He can create a resource by himself, which we call candidate resource. And the only value of this resource is this IP address and port that he received from when he looked for it. It's not a sensor value or anything else. It's just this IP address and port. So he's creating those, and then he's creating a link for that, a resource link. And here you have, so the link URI contains this IP address and port. Define a new relation, which we call candidate. And the anchor, so this is actually, you can link this URI or this link to a real resource. I talk about the sensor resource link, but this could be whatever other things resources you expose. So basically, you can say that this is a candidate for this resource. So that's the first way of doing it. And then you're going to register both of these to the resource directory. And this is where the resource directory comes. You register these resource links to a resource directory, and then other endpoints can fetch those. So that's the first way of doing it. The other way is that you take your register sensor, your sensor resource link, and you put the IP address or this candidate information directly into the URI of that.
So you replace whatever this local IP address and port that the resource link contains with this candidate IP address and port. There are pros and cons for both of these methods. I will not go into those here now because of time issues, but you can do both ways. And then whoever wants to contact you, basically the one that's going to use this candidate. So he fetches this from a resource directory, normal procedures. Now in the first alternative, he will fetch both the resource link for the candidate and there's, for example, the sensor resource link. And again, you have this anchor and this, so you can map these together. So you know that this is a candidate for this resource. Then he will replace, when he's going to send a GET to read the sensor value, he will put the candidate into this link URI, and then he will send the GET. Normally he would try to send it directly here, but now he would send it to this address here, and hopefully it will reach. So you can read the sensor value there. And the other way is that this is going to where there's nothing new here. If the sensor resource link already contains the candidate, the IP address and port, he's just going to use normal resource director procedures. He's going to fetch the resource link associated with the sensor, and he's going to send a GET, and hopefully it will reach. Here is a flow showing the same thing. First, you have the first device number one. He's the one who's actually going to fetch and distribute his candidates. So he contacts this T-Stan server, gets his this public IP address and port, this server reflects it. Then his he's using this embedded for clarity. He's using embedded, so he gets this. And then when he registers his sensor resource link, instead of putting his own IP address and port, he actually puts this into the co-op message. And here it seems to be that public. Yeah, exactly. I'm sorry for that. Yeah. And actually he doesn't. He uses the mechanism. I'm sorry. So he registers his sensor resource link using his normal IP address, but then he also registers this candidate. Yeah, sorry for that. Yeah, and here you see here he actually includes this candidate IP address, the relation this candidate and the anchor. And here this IP address port is the same one as here. So this is how it links them together, right? Because you need to know, because there may be multiple devices subscribing. You don't really do anything with a candidate unless you know what you can use it for, right? So that's actually, so this was the first step. This is how he distributes the candidates to the. And again, if you would use the second method, you would put it directly here into the sensor resource link, the NAT address, and you would skip this step. The other one, then you have device 2. Yes?
Comprehensive what ensures that the NAT actually keeps that port open, or that this pin is the one where the device will be.
Like I said earlier, you will have to send these keep alives, obviously, if you're using this. You will have to send keep alives. And this is what I said. Normally, the way it works in ICE, you will send the keep alives to the same place here. Now in ICE, you can send keep alives without getting any reply. Basically, you can send an empty UDP packet or something like that, or a stun indication. The good thing about sending a request which actually trigger a response is that you will always get this back. So you will see, for example, if the NAT binding has gone down or if it has created a new NAT binding. So that's always a choice you will have to. If you don't care or if you trust it's not going to be done, you can just send something simple, which is not going to cause so much processing.
Okay. But it's then really every 20 seconds or something like this. That was kind of the observed time.
I don't think the NAT bind, well.
That's 30 seconds what I saw. So it's really...
Yeah, well, of course, like I said in the beginning, I skipped that for here. If he's controlling the NAT, he's supporting TCP or some of these protocols, then he obviously doesn't need to support. But then, of course, he's not going to need to contact him either because he will get his public IP address support from here directly. Yeah.
I was just going to say, this looks like really, really strong argument, right?
Yeah, I didn't want to go there. I wish I had one of my colleagues working for a big.
So the reason I would say that actually it's not beyond the realm of possibility. IoT devices being segmented a lot more. Actually,
IPv6 is going to reduce some of the need for this, but it's not going to.
Please do publish this, right? Because it'll actually encourage the people that will be able to pick their poison, right?
Yeah. So, but anyway, yeah. So, sorry. Yeah.
There's also a case for
You're absolutely right. The ULA, mining for ULA can last a long time. You don't have to worry about it. It's a lot simpler architecture. I mean, you're doing what you have to do given up.
Yeah, and sure, and I mean there are other reasons why people will maintain NATs also in IPv6, but maybe this is not the. I'll try to. But anyways, yeah. So I'll just sorry for rushing, but I'm trying to. So then device 2, he wants to contact him, and now obviously there is an NAT here, so he will not be able to contact him using his local IP address. So then he's using again normal resource directory procedure. He wants to have a temperature sensor link. He gets that one back. Then he's asking for a candidate, which again using the anchor, which is associated with this one. He gets this one back. This is the public IP address support and everything. And he takes this one, puts it into the GET, and sends it here. It may reach and may not. Obviously, you have different NATs can be, some are more restricted than other where they're gonna let traffic through. But again, like I said, there are relays and other things. But this is the basic idea. He gets the code, they get this, and then he sends the response back with train 23 or whatever the temperature value is. So this is basically the use case, normal co-op usage. This is not about setting up a real-time media stream or anything between these two devices. This is basically using the resource directory, trying to find the resource links for the data he's interested in, temperature, for example, or whatever, and then contacting the guy who is behind the NAT. Obviously, he may also be behind the NAT, so he may do the same thing, registering his candidates and everything.
Well, does he find out that the device one has it?
These are, of course, into the details. You could, of course, have put their information. Yeah, also, I also have a candidate that you may want to look for. But here, I'm just assuming he gets this, and then he just sends this and asks, hey, by the way, does he also have a candidate? Is there a candidate, one or more candidates associated with this anchor? If it wouldn't be, then he would, of course, send 4 or something. But in this case, he comes here.
Actually, could observe.
Sure. Yeah, I mean, yes. Now, again, trying to keep it simple, he's asking for it once. And if he's only interested in accessing him once, he wouldn't observe. But if he's going to do it more often, yes, he could make an observation, and then he will get it. And if, for example, he notices when he does his thing here that he gets a new IP address or a new candidate, he will update it, the registration, and then he will get a notification about it. Yes. Yeah, and these were I mentioned all of this already, so that was kind of be nice in a nutshell. The semantic is interesting things here, and I mentioned, for example, I said you have this reflexive resource. This was the resource where you send your get and it reads your value. So this is kind of interesting because, like I said, it doesn't have a value all the time that you read, for example, a temperature value. It gets the value when it receives your request, and then it sends that back. And it's going to get a new value when it gets a request from someone else. Then you had a candidate resource, which basically, so this is not a value representing anything physical in the endpoint. It's not a temperature or battery or anything. It's this value which is assigned by the NAT, or a relay or whatever you get your public IP address from. And then maybe the most interesting is this candidate resource link, because as we know, the resource links, they don't provide, typically they don't provide the resource value, right? They just get the link. This is from where you can get the value, and then you get the certificate and get the value. But of course, in this case, because the value, the IP address, the NAT IP address support itself is actually the value of the resource. And since you're going to put that into the resource link URI, it's actually you are going to provide value in the resource link itself. So that's kind of interesting aspects of the whole thing. And like I said, yes, there's a new link relationship, which is called candidates. Then you use this anchor. I mean, this could be other ways to do this. So I think that's all I had. And it went very quickly, but I wanted to do the best. So again, I'm also going to be at the hackathon. So if anyone is interested in this, talking about it, is this something we should maybe? There is no draft about this. So this is just representing the study I've done. So forwarding one way or another.
One question. How do you find out that
those are discovery. Yeah, like I said, the distance server is just a hub server hosting a specific resource. It's just a resource.
You define the resource type in the graph.
Yeah, I called it. Where was it? Fetch. I called it reflexive resource. Yeah, this is what I called it. This is basically the resource where he is addressing his.
Probably you can get you to find out that the resource is
exactly. And of course, this could be maybe this could be. I mean, this is just a function. This could be the resource directory itself. Also, or it could be anywhere. I think in ICE normally to utilize this is something you normally configure.
It's interesting to get discover it outside your NAT. So not just like you can't just do a broadcast. That's the point. You have to actually get to the NAT and then find it. You discover things outside your NAT.
Inside resource directory might have a link to the outside resource directory. That's just that sort.
Right. I'm just saying it's not, you can't just do MDS.
Yeah, and this obviously has to be the public network. This is also so the devices behind the network. Because they need to go through the NAT. So,
one of the earlier spots I remember who mentioned, but like that also being one of the big issues for IoT. So here is one potential solution. This is of course rather heavyweight because that kind of solves various different kind of curious topologies with NATs. They are simplified 5 ways to have more simple scenario. But this something has been well tested, tried out of concept level of the multimedia space, how to control the generate is how it could be applied.
I do want to say it's when it's done and turned, and a lot depends on what your ISP cooperates with the whole environment, right? So act as a public network, whether you can actually reach you need to get to
sure, there may be other policies in the network which
exactly.
exactly.
About half the time.
I mean, this is you should definitely publish something on this because really go to town on just why people should have IPv6. I mean, in this particular use case for IoT, and I'm not joking. There are all sorts of reliability issues that NAT brings into especially in the service provider or CGNAT, right? Lack of transparency there is harmful if the server actually has to, the device actually something that actually has to work reliably.
Well, I think what's really interesting here is analyze the failure modes.
Yeah.
What are all the things that go wrong? Right? What if the IoT blocks this NAT changes very frequently? So,
or the NAT reboots, or loses state. What's in the directory in one
I
place?
think looking at the ways that go wrong, trade-offs, relative costs, using rigorous stun time, for example, versus the lightweight version. You have these UDP messages, what if you use some discuss that, but as soon as you use UDP, you should drop that network.
And obviously the trust that some service.
Sorry?
Resource. To the correct
Sure. I mean, you need. Yeah. That's a good one.
So if you have a malicious stun server, could it like redirected traffic?
Yeah, I mean, in stun, you have all use authentication and those kind of things. So maybe that's something that they're too, but you know, understand. Do people think this is? I assume the first place for this would be maybe this research group before going.
No, it's something we could do in core.
I would start. I would really start right up the use case. Now, for you guys want to work with. That's a good introduction to another specification.
Right? I can talk with the chair about that and see what that is. As long as I want to see first, because otherwise I think it's
Right, but I was going to say have the use case out there. So, for instance, for multimedia, it's not clear that this is at this point it's just multimedia. But for say real IoT use case, I suspect that once you're crossing a NAT or you're expecting to cross a NAT, what you're really doing is you're running a cloud-based service. What? But if you're expecting to cross that boundary, then what you really want to go for is probably doing a cloud-based rendezvous, which is it's a different, in a way, it's an evolution on stuff.
you could use that for this too. I mean, obviously, as long as the device, as long as this could of course be a cloud server. And as long as the device behind that is the one initiating the connection, right? Then you don't need any of this because he's going to be the public network and he will initiate the connection and he can have his queuing and get it whenever he gets something. But again, if he wants to establish a connection with the device one, the one that's behind that, you could use this mechanism for that too.
Yeah. But what I'm getting at is that I think for most of these use cases where the NAT is involved, probably what you're doing is having the resource advertised through whatever cloud-based service. And so what all they do is everybody just connects the cloud-based service to the cloud service routes and you just triangulate it out. The only times that doesn't work is when you have a vast amount of bandwidth involved or where latency has to, you really have to be able to have a latency problem that is greater than 500 milliseconds. It's a pretty any decent cloud-based service, that's a lot of time. So I think the challenge here will be exactly what question you asked, which is there a real use case here? if I look at the way that we're implementing video, this WebEx, everything's going through central servers. Nothing's going peer to peer. The same is true with most of the RTC. So now the question really is, is this something that might be an industrial setting or a smart city setting or something like that?
Even the smart home, one thing that we see is a lot of multiple vertical silos going through cloud services unnecessarily. A lot of them
necessarily.
What is the evolution to more local connectivity and professional? Look at Mozilla, whatever thing, you have a local, a rule manager, whatever. A lot of those are behind the NAT. What do you have local NATs in the home environment or want to have a segmented network?
So on the whole, right, if you look at the way Google has gone with their APIs and a lot of other people with their APIs, that's absolutely nothing to do. It's not peer-to-peer. It's all public to cloud.
I know that. They want to sell cloud services.
Right. Well, but not only that, but there's good reason for it. The whole reason for that model is to reduce costs in the device. And there's actually a lot of environmental benefit.
Well,
I think what you're saying, you're questioning the whole concept of resource factory.
In the home. I feel differently elsewhere. Like, I think the resource directory model for the industrial, for building automation space, I think that's stronger. But in the home, I don't see it happening. Precisely because right now there's a lot of ecosystems. Everybody's going up to their clouds. They're doing some cloud-to-cloud communication, some API building on top. If that sounds like it's a bad thing because you don't end up with an openly droppable world, maybe I'd cop to that point. But there is this benefit that I've just reduced my memory usage on those devices by maybe 60%, maybe more, maybe 80%. And in doing so, and I might even reduce my processing requirements on that device by a similar amount, which is power consumption.
I'm not convinced that going to the cloud reduces the power consumption on small devices. It increases them to be able to support, more complex stacks, handle the traditional internet.
So there's a researcher at Berkeley who I think should be looking at that problem, looking at related problems. He used search enablement. Search just did. We're getting off into so I'll take that offline.
You can discuss it over.
Thanks for the presentation.
And that gives us 3 minutes for final discussion and conclusions. And we will
We have a little logistics item. So those people who want to continue talk about this can meet today at 7. Which is in the same building as the 2 IETF meeting address in the basement number 1. So 44E. And we have a table for 16 here. Here. So you can come.
Actually, I'm sorry. I didn't say I was going to go, but
Yeah.
I thought it was going to be around here. Until tomorrow, I'm actually at 99 university. So I'm not going to go to dinner. Or it's been done in Canada about process. That's correct. But anyway, so I'm sorry, guys. It's very what you guys have.
So here we take the one year.
Well, you can have my right if you want.
Thank you.
Absolutely. That's not what my case is.
Besides dinner, is there any other follow-up one to establish? I guess for me tomorrow,
Well, I have a suggestion. You know, I was the last person involved there. And I think there's a lot of references. What's missing? I think you got that one. You saw the people have a real use case and show how these different models work in reality. A lot of this stuff is extremely theoretical, we went through protocols and this and that, but maybe that's what you're going to do. But it would be really nice to say, okay, this is one industrial example, because we talked a lot about that, and this is how it actually works in reality, and that would be really
yeah, I agree. The focus on that, but still going to be looking at artificial use cases. What you're really going to do is collaborate with, you know, the smart city POC project, put the gears to evolve. I think a very good thing to get involved in. IIC also runs test beds.
I have the use case that I could actually run, but I don't know.
Right, but and we've got like medium size, all of the medium sized projects, but it still doesn't get to the idea of scalability. How do I roll out devices management? That's where I'm getting involved with the smart city project. For example, work on. We really, you know, level up a lot of this.
Yeah, no, they have 1,000 students.
Well, actually, universities are good medium sized, medium large scale projects.
They have cheap labor.
Cheap labor, business scale, building campus scale problems. Campus is really small cities.
These people we working with, when you're doing wireless, and we had to change the battery. You have a lot of students, it's like all of them.
Is there any groups or institutions like established?
One of the things still actually just finishing the standardization process. And so, you know, they are basically proof of concept at this point, but not really product, but looking at standard. There are, you know, things in works. The next step is to kind of get the products. And there are places to say, here's the blank where we drop in the metadata. Right? And so there's a place where we need like need a standard for it.
Additional questions. How long? I know it could be an estimate or months or years to standardization.
That's done.
Yeah, so I think one of the things is the final stage kind of standard. I know basically it's standard every year. But we also know there's been this work on the other version of it. I think some other things are already standards, like all four stuff. They may not have dealt with some parts of it. Right? There's a lot of things that come up with modular standards. One piece is done, but it assumes other parts not finished yet. So I think that what I've been working on, though, with other things, is kind of integrated with stacks, like projects, right? Where it would make sense to have the rest of the pieces.
I guess adding on top of that, like, let's say an institution were to like or use the standard systems. They're on like a big one module or another piece of it. The difficulty I see with that is that they be easily changed and early adoption might.
Yeah, well, I think here it's kind of like the light green problem. And, you know, there's, you know, you're gonna adopt them early, you're early adopter. There's some risk that that is the wrong choice and that you, that's the wrong thing. this is why you do a relatively small scale POC, right? Is you're testing it out, it works, and then before you roll it out to the larger scale.
So I think some of this probably really working your head is already. Case in point, the art on mud for a moment. Even if you do not implement a single automated feature in your network from a perspective, just having a declaration for your developers about what sort of access their device is required, the formal, if you test them and say, do you know? Because if they don't know, how the heck are you supposed to be assured that the access to the
Likewise, the description, there's no tool, it's formal documentation. What devices do.
right, which is useful. Exactly. So, and this we should talk more about how mud and pig descriptions come together. If you wanted to, because this also ties to another effort that's going on in this, which is somewhat nation. It may even be misguided, to be quite honest, which is the idea of software builds and materials. And so the idea of a software build materials is that if you have an IoT device that has a large number of software components, how do you know if there's vulnerabilities? Mud is all about vulnerabilities, protecting against vulnerabilities, and the fact that like just saying you have a printer doesn't tell you whether you have a vulnerability. Saying you have an HP 4000. Sorry. Right, so this is, yes, you're using, but say people are in the room. Okay, so while the miner is in the room, for instance. And
this is one of the weaknesses of the virtual application. That's what a lot of things that don't know it. Because there's massive stuff on
and then there's the relationship between the two. So for instance, how might the software build materials help build out the thing description, or vice versa?
Right. So I think the whole issue of software packaging is something that we can talk about executing. It's really important for containers and everything. And even tooling your NPM right now on that automation. But just to put it aside, the more general problem is the problem of how do we avoid reinventing the wheel? So the standards landscape is so complicated, right? That there's this investment time you have to take just understanding what's out there, right? And figure out how to put it together.
Not only what's out there, but get some technical what each of them actually does.
Right. I think I've been spending a lot of time on this just to understand the pieces. So I wonder how we can do better at that. Yeah, that was like, so we put his brain in the bottle.
So what's interesting about this, right, is I could imagine a thing description where I could take the thing description, generate essentially an intermediate form of a mud file. It says here, well, based on the fact that we use protocols, protocol bindings, here's the access that's needed. You just need to fill in the endpoint.
More generally, I have a set of things that change. I have some rules for how they connect. From that, I infer what are the necessary network configuration and put those things together in that way.
Yes.
And then the network can enforce that policy so that someone can't notice things they're not going.
Right. So MUD is actually based on the access control model. So you could actually skip the MUD part if you want, and just use the access control, the underlying access control model. That purpose, and that would be perfect.
And I don't think we answered the question. The question is, the only confusion is that these overlaps, many of them don't prepare properly what to do at home. I advise somebody to do this. First of all, articulate your system requirements and assumptions in the code that you have and whether you are picking those and whether you are buying them. If you are buying them, very cool. File this. And you are giving them any kind of full similar standard architectural topical values from them. I understand that the head probably.
Also, the whole idea of document requirements is that's super useful for us. Where the gap was needed, what the missing pieces.
That's why I was asking about whether having an example of showing it works this way.
So we've got actually hundreds of devices. The test is I can point you to a database of in-state restriction. I think what's missing though is more open source implementation of the actual thing. I have some, but I haven't done the process of open sourcing them.
Okay, so we
Thank you for
Well, sorry for the, we didn't have much fun, guys.
Oh, that's
next.
Nobody mentioned the logistics of getting back. We have a hop on last time.
Well,
Each man after himself.
so downstairs receptionist, there was a number for a grab.
Those who had, yeah.
Yeah, transit map, the A2 back to the MRT, the MRT pack, I suggested a harbor front and.
I think if we want to share the gap.
Okay, yeah, we'll go on to your cab. I think the MRT.
Yeah, let's.
the only one.
I was thinking of grabbing a grab. I could take a couple people. I'm going to the Fairmont, which is right next to it.
Oh, so I'm going to a call.
So, we're going to Fairmont, Swiss or the.
Swiss and Fairmont are next.
So we're.
I'm also
Okay. That's us meet at the lobby.
Okay.
And I check our last.
I mean, actually, between the six of us, between a cab and grab, it almost makes a difference. Cost.
Right, as you know, there's lots of that.
Okay, thank you also for everyone joining online. We're signing out here. Bye bye.
Charge.
All right, so we'll see people downstairs.